Hello, and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly into one of the simplest yet most profound questions we can ask about our cosmic home. Tonight, we're going to explore something that sounds straightforward at first, almost childlike in its directness, but unfolds into layers of wonder the more you consider it. We're going to ask, just how big is our galaxy? How vast is this structure we call the Milky Way? This pale river of light stretching across dark skies? This system of hundreds of billions of stars that includes our sun, our planet, and everything we've ever known? The question seems simple until you realise we're asking it from the inside, like trying to measure an ocean while swimming in its depths, unable to see the shores, unable to rise above the waves. We're embedded in the very thing we're trying to understand, and that makes the answer both more difficult and more intimate than it first appears. Here in this space between waking and rest, we'll wander through the history of how humans learned to measure the immeasurable, how we piece together clues from starlight and motion, from mathematics and patience, until slowly the true scale of our galaxy emerged from darkness into understanding. We'll discover that size is not just a number, not just a distance measured in light years, but something richer, something that encompasses structure and time, motion and mystery, the visible and the invisible woven together. Each episode here isn't about memorising figures or impressing with technical terms. It's about letting scale wash over you gently, about feeling your place within something so vast it makes daily worries shrink to nothing, about understanding that you are not separate from this immensity, but part of it, carried along in its quiet turning. If you enjoy these journeys into cosmic perspective, a like and subscribe help this channel continue. But for now, you don't need to do anything but listen, breathe, and let the vastness settle around you like a blanket of stars. The question of the galaxy's size has haunted humanity for as long as people have looked upward into darkness and wondered. Long before telescopes, before the scientific method, even before written language, our ancestors saw the Milky Way stretching overhead like a river of pale light. They told stories about it, wove myths around its presence, but they could not measure it. They could not know what it truly was or how far it reached into the black between stars. For most of human history, the Milky Way was simply there, a mystery accepted but not understood. Ancient cultures gave it names that reflected how it appeared to them. The Greeks saw spilled milk across the heavens. Chinese astronomers called it the Silver River. Norse myths described it as a bridge between worlds. Each culture recognised its presence, its beauty, its strangeness, but none could answer the fundamental question of scale. How big was this thing? Was it close or distant? Did it have edges, or did it stretch forever? The setting for our story truly begins in the 1700s, when astronomers first started to approach the problem systematically. By then, telescopes had been invented and improved. Observers could see farther than ever before, could count stars in different directions, could begin to map the heavens with some precision. But the challenge remained enormous. Unlike measuring the distance to the moon, or charting the orbits of planets, measuring the galaxy meant measuring something that surrounded you completely, something you could never step outside of to view from a distance. William Herschel, working in England in the late 18th century, was among the first to tackle this systematically. He built large telescopes and began counting stars in different directions across the sky, reasoning that if more stars appeared in one direction, the galaxy must extend farther that way. His method was simple, but laborious. Night after night, he pointed his telescope at different patches of sky, counted what he saw, and recorded the numbers. His sister Caroline assisted him, writing down observations as he called them out, the two of them working in cold darkness, patience stretched across years. Herschel's conclusion, published in 1785, suggested that the Milky Way was a flattened disk of stars with the sun near its centre. He estimated it might be several thousand times wider than the distance from Earth to the nearest stars. This was the first real attempt to give the galaxy dimensions, to transform it from myth into measurable reality. His estimate was too small, limited by the technology of his time and by dust clouds he could not account for, but it was a beginning. For the first time, someone had tried to answer the question with numbers rather than stories. The setting of this investigation was not just physical observatories and cold nights at the telescope. It was also intellectual, a shift in how humanity thought about its place in space. Before Herschel and his contemporaries, most people assumed the visible universe was relatively small, perhaps only a few thousand stars scattered across the heavens. The idea that we lived inside a structure containing millions or billions of stars stretching across unimaginable distances was radical. It required not just better instruments, but a willingness to accept that the universe was far larger than human intuition suggested. As the 19th century progressed, more astronomers joined the effort. Telescopes grew larger, and photography began to replace the human eye, allowing fainter stars to be captured and studied. Spectroscopy emerged, letting scientists analyze starlight to determine composition and motion. Each new tool added pieces to the puzzle, but the central question remained frustratingly difficult. The galaxy was immense, yes, but how? Immense? Where did it end? Was there anything beyond it? The setting for understanding the Milky Way's size was also shaped by what astronomers could not see. Between Earth and distant stars lay clouds of dust and gas that absorbed and scattered light, making far regions of the galaxy nearly invisible. For centuries, these obscuring clouds hid the true extent of the Milky Way, like fog hiding a coastline. Observers could see only part of the structure, and from that partial view they had to infer the whole. It was like trying to map a city from inside a single building, with windows facing only certain directions and many of them fogged over. By the early 20th century, the question of the galaxy's size had become one of astronomy's great challenges. Competing theories offered different answers, sometimes differing by factors of 10 or more. Some thought the Milky Way was the entire universe, with nothing beyond. Others suspected it might be just one island of stars among many scattered through space. The setting was one of uncertainty and debate, of passionate arguments and careful measurements, of scientists dedicating entire careers to chasing an answer that seemed always just out of reach. This was where the story truly begins, in that era of wonder and frustration, when the tools were finally good enough to glimpse the truth, but not yet powerful enough to see it clearly. The galaxy stretched above them every night, vast and silent, holding its secrets while patient observers tried to measure the unmeasurable. The spark that truly illuminated the galaxy's scale came not from a single observation, but from a gradual realization that spread through the astronomical community like dawn light touching distant peaks. For centuries, the pale band of the Milky Way had been visible to anyone who looked up on a clear night. But what was it really? Was it a cloud of glowing vapour, as some ancient philosophers thought? A concentration of distant fire? A crack in the celestial sphere through which heavenly light shone? The breakthrough came when Galileo turned one of the first telescopes toward the Milky Way in 1610. What he saw astonished him. The hazy band resolved into countless individual stars, far more than the eye alone could perceive, packed so densely that they blurred together into a continuous glow. This was the first true discovery, the moment when humanity learned that the Milky Way was not a cloud or mist, but a vast collection of stars, each one potentially a sun like our own. This realization sparked a new mystery. If the Milky Way contained so many stars, how far did they extend? How deep was this sea of suns? Galileo could not answer these questions, but he had opened a door through which others would follow. The discovery that the Milky Way was made of stars transformed it from a vague celestial phenomenon into something that could potentially be measured, mapped, and understood. As telescopes improved over the following centuries the mystery deepened rather than resolved. Observers found that no matter how powerful their instruments became, the Milky Way always revealed more stars beyond the ones they could already see. It was like looking into a forest where every tree you count reveals two more behind it, stretching into dimness without apparent end. The band of light circled the entire sky, suggesting that we were somehow inside this structure, rather than viewing it from outside. But what did that mean for its size? The discovery that we live inside the Milky Way rather than observing it from a distance was both liberating and constraining. Liberating because it meant we were part of something grand, embedded in the very structure we sought to understand. Constraining because it made measurement extraordinarily difficult. You cannot easily judge the size of something when you are trapped within it, when every direction you look shows you only a slice of the whole, when distance and dust conspire to hide the farther reaches. In the 1800s, a critical discovery emerged from studying star motions. Astronomers noticed that stars near the Sun were all moving in roughly the same direction relative to more distant stars, like a school of fish swimming together. This suggested that our local neighbourhood of stars was part of a larger system rotating around some common centre. The Milky Way was not just a loose collection of stars scattered randomly through space, but an organised structure with motion and mechanics, something that turned like a great wheel through the cosmos. This discovery of rotation sparked intense investigation. If the galaxy rotated, there must be a centre around which everything turned. Where was that centre? How far away? By measuring the speeds of stars and comparing their motions in different directions, astronomers began to triangulate, to narrow down possibilities. The centre seemed to lie somewhere toward the constellation Sagittarius, where the Milky Way appeared brightest and most crowded. But the distances involved remained frustratingly unclear, hidden behind veils of intervening dust. Another crucial discovery came from mapping globular clusters, those dense spherical swarms of ancient stars that orbit in the galaxy's halo. Harlow Shapley, working in the early 20th century, measured distances to dozens of these clusters and found they formed a roughly spherical distribution around a point far from the Sun. This distribution suggested the Sun was not at the galaxy's centre as Herschel had thought, but far out in the suburbs. The galaxy was much larger than previously estimated, and we occupied an unremarkable location within it. This realization was revolutionary and humbling. Not only was the Milky Way immense, but we were not at its centre. We were peripheral, orbiting in the outer regions of a system far grander than imagined. The discovery shifted humanity's cosmic address from centre stage to a quiet corner. Demotion that paradoxically expanded our sense of the universe's scale. The true spark of mystery, however, came from observing spiral nebulae, those faint fuzzy patches scattered across the sky. For years, astronomers debated whether these nebulae were clouds within our galaxy or separate galaxies far beyond the Milky Way's bounds. The answer would determine whether the Milky Way was the entire universe, or just one galaxy among countless others. This question, known as the Great Debate, raged through the early 1900s, dividing experts and sparking passionate arguments. The mystery was resolved in the 1920s when Edwin Hubble used the new 100-inch telescope at Mount Wilson to observe Cepheid variable stars in the Andromeda Nebula. These stars, whose brightness pulses regularly, had a known relationship between their period and luminosity. By measuring how bright they appeared and comparing it to how bright they should be, Hubble calculated that Andromeda lay nearly 1 million light-years away, far beyond any reasonable boundary of the Milky Way. Andromeda was not a nebula within our galaxy, but a galaxy in its own right, comparable in size to the Milky Way itself. This discovery transformed everything. The Milky Way was not the universe, but one island among billions, each separated by vast gulfs of nearly empty space. The scale of existence expanded 1 million-fold in a single revelation. Our galaxy, immense as it was, became just one structure in a cosmos of unimaginable extent. The spark of mystery ignited by Galileo's first telescope had led, over 3 centuries, to this profound expansion of cosmic horizons. The discovery was both answer and new question. Yes, the Milky Way was vast, containing hundreds of billions of stars spread across tens of thousands of light years. But it was not alone, not unique, not the totality of existence. Understanding its size meant also understanding its place among other galaxies, its membership in a larger community of similar structures. The mystery of scale had deepened even as it was partially solved, revealing that every answer in astronomy opens doors to larger questions, grander mysteries, deeper wonders waiting in the dark. When astronomers first began to grasp the true scale of the Milky Way, the response was not immediate acceptance, but a mixture of awe, disbelief, and profound disorientation. The numbers defied intuition. Distances measured in thousands, then tens of thousands, then hundreds of thousands of light years stretched the imagination beyond breaking. How could something be so large? How could we live inside it without sensing its immensity? The human mind, evolved to understand distances measured in steps and stone throws, recoiled from figures that dwarfed entire planetary systems. Early reactions often took the form of skepticism. When Harlow Shapley proposed in 1918 that the Milky Way might be 300,000 light-years across, many colleagues dismissed the estimate as absurdly large. His measurements of globular cluster distances suggested the galaxy was 10 times bigger than previous estimates, placing the Sun far from any central position. Critics questioned his methods, his assumptions, his data. Surely the galaxy could not be that vast. Surely we could not be so far from its centre. The psychological resistance was as strong as the scientific objections. Even those who accepted the new measurements struggled to internalise what they meant. Astronomers could write the numbers, could publish papers detailing distances and dimensions, but translating those figures into genuine understanding proved nearly impossible. A light year itself was already beyond easy comprehension, nearly 10 trillion kilometres of empty space. Multiply that by 100,000, and the result became abstract, a mathematical construct rather than a graspable reality. Scientists found themselves in the strange position of knowing something intellectually, while being unable to feel it emotionally. The awe came in waves, often during quiet moments away from calculations and instruments. Sitting under dark skies, staring at the Milky Way stretching overhead, astronomers would try to picture what they had learned. That pale band contained hundreds of billions of stars. The photons entering their eyes had travelled for thousands of years from sources so distant that entire civilizations could rise and fall in the time it took their light to arrive. Every faint smudge visible through a telescope represented an inconceivable congregation of suns, each potentially hosting planets, each burning for billions of years in the silent dark. Some responded with poetry, attempting to capture in words what mathematics could describe but not convey. Others retreated into numbers, finding comfort in precise measurements even when those measurements pointed toward the incomprehensible. A few experienced something like vertigo, a dizzying sense of scale that made daily concerns feel absurdly small. Standing on a planet orbiting a star in the outer regions of a galaxy containing hundreds of billions of similar stars, each human life became simultaneously insignificant and miraculous, a tiny spark of awareness within an ocean of space. The disbelief manifested in persistent challenges to new findings. When improved measurements in the mid-20th century revised the Milky Way's size downward to roughly 100,000 light-years across, some felt relieved. A smaller galaxy, while still enormous, felt more manageable somehow, less threatening to human significance. But even this revised figure remained so large that most people could not truly grasp it. The difference between 300,000 and 100,000 light-years was lost in the general immensity, like arguing whether an ocean is impossibly deep or merely unimaginably deep. Public reaction, when the discoveries filtered beyond academic circles range from fascination to indifference. Most people went about their lives unchanged by the knowledge that they inhabited a galaxy of such scale. The stars still looked the same, the night sky still turned overhead, and the vast distances revealed by science remained invisible to the naked eye. For some, this created a strange disconnection. How could something so important, so fundamental to our cosmic address, have so little impact on daily experience? The galaxy could be 100,000 light years across or 1,000,000, and breakfast would taste the same. Yet for those who took the time to contemplate what had been discovered, the response often shifted from disbelief to a strange sort of comfort. Yes, the galaxy was incomprehensibly large, but it was also stable, ancient, enduring. Its scale made human troubles seem temporary and small by comparison. Wars, disasters, personal failures, all the dramas that filled individual lives occurred on a stage so tiny that from the perspective of the galaxy they barely registered. This was not nihilism, but perspective, a way of situating suffering within a larger context that could make it more bearable. Astronomers themselves developed coping mechanisms for working with such scales. They created mental models, analogies that made the numbers more tractable. If the galaxy were shrunk to the size of North America, the solar system would fit in a coffee cup. If individual stars were grains of sand, the Milky Way would fill several Olympic swimming pools. These comparisons were imperfect, but they helped bridge the gap between abstract knowledge and intuitive understanding, giving the mind something concrete to grasp. The emotional response also included wonder, pure and undiluted. To realise that the faint glow stretching across the night sky represented the combined light of billions of distant suns was to touch something sublime, something that transcended ordinary experience. This wonder was not diminished by scientific understanding, but enhanced by it. Knowing how vast the galaxy truly was, knowing the physics that governed its rotation, and the chemistry that built its stars made it more marvellous rather than less, revealed depths of complexity and beauty invisible to casual observation. Some astronomers reported moments of profound connection, instances where the intellectual knowledge of the galaxy's size merged with direct experience under starry skies. In those moments, the numbers fell away, and what remained was a direct sense of participation in something immense. They felt themselves not as separate observers studying a distant object, but as parts of the galaxy itself, atoms of awareness within a larger body. The boundary between self and cosmos softened, and the galaxy's size became not a measurement but a lived reality. The first response to understanding the Milky Way's true scale was thus complex and layered, mixing skepticism with acceptance, disbelief with wonder, disconnection with profound connection. It challenged fundamental assumptions about humanity's place in the universe, and forced a reckoning with scales that defied everyday intuition. Some turned away, overwhelmed or disinterested. Others leaned in, finding in the galaxy's immensity not threat but invitation, not diminishment but expansion. The numbers themselves were just the beginning. What mattered was how those numbers changed the way people saw themselves, their world, and their place within the silent turning of stars. At the heart of measuring the Milky Way lies a fundamental contradiction, a paradox that has challenged astronomers since they first attempted to determine the galaxy's size. The contradiction is this: to measure something accurately, you typically need to observe it from multiple vantage points, to see it from different angles, to step back and view the whole. But we cannot step back from the galaxy. We are embedded within it, trapped inside the very structure we are trying to map, unable to gain the external perspective that would make measurement straightforward. We are asking the ocean to measure itself while remaining submerged. This creates an immediate problem. When you look at the Milky Way from Earth, you see only an edge-on view, a slice through the disk where your line of sight passes through the greatest density of stars. The band of light stretching across the sky gives you information about the disk as plane, but tells you little about its full width or the extent of the halo. You're seeing the forest from within, counting trees in one direction, but unable to judge where the forest ends because intervening trunks block your view of the distant edge. The scientific method demands objective observation, clear measurements, repeatable results. Yet measuring the galaxy requires inference, extrapolation, assumptions that may or may not hold. You measure the distance to nearby stars and use that to calibrate more distant measurements. You observe the motions of gas clouds and infer the distribution of mass. You map globular clusters and assume they trace the galaxy's outer structure. Each step requires trust in theory, in models, in mathematical relationships that connect what you can see to what remains hidden. Science prefers certainty, but the galaxy offers only probabilities. This contradiction between the need for precise measurement and the impossibility of direct observation has led to centuries of uncertainty. Different methods often produce different results. Measuring distances using Cepheid variables gave one answer, using the motions of stars gave another. Mapping interstellar dust suggested different boundaries than mapping stellar populations. Each technique had its own assumptions, its own sources of error, its own blind spots. Reconciling these competing measurements became as much art as science, requiring judgment about which methods to trust and which to question. The mystery deepened when astronomers discovered that much of the galaxy's mass was invisible. Stars and gas account for only a fraction of the total. The rest exists as dark matter, detectable only through its gravitational influence on visible objects. How do you measure something you cannot see? You observe how stars orbit, how gas clouds move, how light from distant galaxies bends as it passes through the galaxy's gravitational field. You infer the presence of invisible mass from its effects. But this introduces yet another layer of uncertainty, another contradiction between what is directly observable and what must be deduced. The contradiction extends to defining what we mean by the galaxy's size. Do you measure only the bright disk where most stars reside? That gives one number, roughly 100,000 light-years across. Do you include the halo of sparse stars and globular clusters? The galaxy grows to several 100,000 light-years. Do you count the dark matter halo extending far beyond any visible structure? The galaxy might stretch nearly 1,000,000 light-years. Each definition is valid, but gives a different answer. Size becomes not a fixed quantity, but a choice about what to include, a decision about where the galaxy ends and intergalactic space begins. This ambiguity troubles the scientific mind, which prefers clear categories and definite boundaries. Yet the universe does not always cooperate with human preferences for precision. The galaxy fades gradually rather than stopping abruptly. Its density decreases outward until at some point the stars and gas are more influenced by neighbouring galaxies than by the Milky Way itself. Where exactly that transition occurs depends on your definition, your measurement technique, your choice of threshold. The galaxy has no sharp edge, only a gradual dissolution into the space beyond. Science demands that mysteries be solved through observation and reason, that unknowns be transformed into knowns through patient investigation. Yet every answer about the galaxy's size reveals new mysteries. We learn the disk is 100,000 light-years wide, then discover it is warped like a bent record. We map the spiral arms, then realise they are not permanent features but density waves moving through the disk. We measure the mass, then find that most of it is invisible. The contradiction is that solving mysteries creates new ones, that each layer of understanding reveals deeper layers still hidden. This tension between knowledge and mystery is not unique to galactic astronomy, but is particularly acute here because of the scales involved. In laboratory science, you can repeat experiments, control variables, observe from multiple angles. In galactic astronomy, you get one view from one location, and you cannot return in 1,000 years to check if your measurements still hold. The galaxy changes too slowly for human lifetimes, yet too quickly on cosmic timescales to be considered static. You're trying to photograph an ocean from a small boat in the middle of it, using instruments that can only see certain wavelengths, while fog and waves obscure much of what you hope to measure. The contradiction also appears in the gap between mathematical models and physical reality. Astronomers build computer simulations of galaxy formation, testing whether their theories can reproduce what we observe. These models can create virtual Milky Ways, complete with spiral arms and dark matter halos, and measure their properties precisely. But are these virtual galaxies accurate representations of the real thing? How do you verify a model when you cannot step outside the real galaxy to compare? The simulations are constrained by observations, yes, but those observations are themselves incomplete and uncertain. You're using imperfect measurements to test models designed to explain those same imperfect measurements. Despite these contradictions, progress continues. Each generation of astronomers refines the estimates, reduces the uncertainties, adds new layers of detail to the galactic portrait. Modern space telescopes like Gaia measure positions and motions of billions of stars with unprecedented precision. Radio telescopes map hydrogen gas across vast distances. Infrared observations pierce through dust to reveal hidden regions. Slowly, painstakingly, the picture becomes clearer even if never perfectly clear. The contradiction between science and mystery may never fully resolve. Perhaps it is inherent in the human condition, this desire to measure and understand paired with the impossibility of complete knowledge. We live inside the galaxy, made of its matter, subject to its physics, yet somehow separate enough to study it, to question it, to seek its dimensions. This simultaneous intimacy and distance, this being both part of and apart from what we study, may be the deepest contradiction of all. We are the galaxy examining itself, consciousness emerging from stardust to measure the sea of stars from which it arose. As astronomers accumulated observations about the Milky Way, competing theories emerged to explain what the data meant. The galaxy's size became not just a question of measurement, but a battleground of ideas, with different schools of thought proposing vastly different scales based on their interpretation of the same evidence. These divisions were not merely academic, but reflected fundamental disagreements about the nature of the universe itself, about humanity's place within it, about how to properly conduct science when the subject under study surrounds you completely. One early theory, championed by those who followed William Herschel's work, held that the Milky Way was relatively small and that the Sun occupied a central or near-central position. This model, comfortable and reassuring, placed humanity in a privileged location within a manageable cosmos. The galaxy might extend a few thousand light-years, perhaps 10,000 at most, containing millions of stars but remaining comprehensible in scale. Proponents pointed to star counts that showed roughly equal numbers in all directions, suggesting we sat near the middle of the distribution. Opposing this view were astronomers who argued the galaxy must be far larger and that we occupied no special position. Harlow Shapley, studying globular clusters in the early 20th century, proposed a model where the Milky Way stretched hundreds of thousands of light-years and the Sun lay far from its centre. His measurements showed that globular clusters formed a spherical distribution around a point distant from our location, suggesting that point, not our Sun, marked the galactic centre. This theory was unsettling to many, displacing humanity from the cosmic centre once again, but it fit the observations of cluster distances and distributions. A third theory emerged from studying spiral nebulae, those faint fuzzy patches visible through large telescopes. Some astronomers, including Harlow Shapley himself, believed these nebulae were relatively small objects within our galaxy, perhaps new solar systems forming from gas and dust. This model kept the Milky Way as the dominant structure in the universe, large but not necessarily one among equals. Others, notably Heber Curtis, argued that spiral nebulae were actually separate galaxies far beyond the Milky Way's boundaries, each comparable in size to our own. This island universe theory suggested a cosmos far vaster than anyone had imagined. The debate between these theories reached its peak in the Great Debate of 1920, a formal discussion between Shapley and Curtis at the National Academy of Sciences. Shapley defended a large Milky Way with spiral nebulae as minor internal features. Curtis advocated for a smaller Milky Way surrounded by countless other galaxies. Both presented evidence, both made compelling arguments, and neither definitively won. The audience left uncertain, the question unresolved, the theories still competing for acceptance. What made these theoretical divisions so passionate was that they touched on fundamental questions beyond mere measurement. If the Milky Way was the entire universe, then understanding it meant understanding everything. If it was one galaxy among billions, then a vastly larger cosmos awaited exploration. The implications for humanity's significance, the possibility of life elsewhere, for the ultimate fate of existence itself, all hinged on which theory proved correct. The size of the galaxy was not just a number, but a window into the nature of reality. Minds divided also along methodological lines. Some astronomers trusted visual observations, the direct evidence of their eyes aided by telescopes. Others preferred photographic plates that could capture fainter objects and record details invisible to vision. Still others championed spectroscopy, analysing light itself to determine composition, temperature, and motion. Each method had strengths and weaknesses, and each tended to support certain theories over others. The choice of tool influenced the conclusions drawn, creating camps divided not just by interpretation, but by practice. Statistical approaches added another dimension. Some researchers counted stars in different directions and used those counts to infer galactic structure. Others measured stellar motions, tracking how stars moved relative to each other, and using those velocities to calculate the mass distribution and extent of the system. Still others focused on specific objects like Cepheid variables, using their known properties as standard candles to gauge distances. Each statistical method required assumptions, and different assumptions led to different galactic models. The theories also divided over the role of interstellar dust. Some astronomers recognized that dust clouds absorbed and scattered starlight, making distant regions appear fainter than they truly were. Accounting for this extinction was crucial for accurate distance measurements. Other researchers downplayed or ignored dust, either because they did not fully appreciate its effects or because they lacked good methods to measure it. This single issue, dust's impact on observations, led to estimates of the galaxy's size differing by factors of 2 or 3, with profound implications for every other calculation. Competition between theories drove progress. Each camp sought better observations to support their model and challenge rivals. Telescopes grew larger, techniques improved, new wavelengths beyond visible light were explored. The division of minds created a productive tension where claims had to be rigorously defended and alternative explanations carefully considered. Science advanced not despite the disagreements, but because of them, each theory pushing the others toward greater precision and deeper insight. Personal factors also played roles. Some astronomers built entire careers around specific models of the galaxy and resisted evidence that contradicted their life's work. Others embraced new data eagerly, willing to abandon previous positions if observations demanded it. Generational divides appeared, with younger researchers more open to radical ideas, while established figures defended traditional views. The sociology of science, the human dynamics of reputation and rivalry, shaped which theories gained support and which were marginalized. The resolution came gradually rather than suddenly. Edwin Hubble's observations in the 1920s showed definitively that spiral nebulae were distant galaxies, settling the island universe debate in Curtis's favour. Improved measurements of interstellar dust led to revised distance estimates, bringing Shapley's model closer to reality, while reducing his initial size estimates. Better understanding of stellar populations of how stars of different ages and compositions distribute through the galaxy, refined the picture further. No single observation or argument ended the theoretical divisions, but weight of accumulated evidence eventually pushed consensus toward a particular range of sizes. Even today, theoretical divisions persist about details. How far does the dark matter halo extend? Where exactly does the Milky Way end and the Andromeda Galaxy's sphere of influence begin? How massive is the central black hole? These questions generate competing models, each with supporting evidence, each with uncertainties. The mind continues to divide over specifics even as broad agreement emerges about the galaxy's general scale. The lesson from these theoretical battles is that measuring the galaxy's size was never just a technical problem, but a scientific, philosophical and human challenge. Different theories reflected different values, different methods, different visions of what the universe might be. The divisions pushed astronomy forward, forcing rigour and creativity, demanding that claims be tested and alternatives considered. Through debate and division, through competition and collaboration, the immeasurable slowly became measurable. The pursuit of the galaxy's true size required more than theories and debates. It demanded action, investigation, the patient accumulation of data point by data point across decades. Astronomers mounted systematic surveys, built ever larger telescopes, developed new technologies to pierce through dust and distance. The investigation became a collective effort spanning generations, with each new discovery adding a piece to an enormous puzzle that was only gradually revealing its full picture. The first major investigative tool was the photographic plate. Unlike the human eye, which can observe only briefly and remember imperfectly, photographic plates could accumulate light over hours of exposure, revealing faint stars invisible to direct vision. Beginning in the late 19th century, astronomers systematically photographed different regions of the sky, creating archives of images that could be measured and analysed at leisure. These plates captured not just positions but relative brightnesses, allowing researchers to identify different types of stars and estimate their distances based on how dim they appeared. Spectroscopy emerged as another crucial investigative technique. By passing starlight through prisms or diffraction gratings, astronomers could spread it into component wavelengths, revealing absorption lines that indicated chemical composition and temperature. More importantly, measuring shifts in these lines revealed how fast stars were moving toward or away from Earth. This Doppler shift information allowed investigators to map the galaxy's rotation, showing how different regions moved and inferring from that motion how mass was distributed. Stars near the galactic centre orbited quickly, those farther out more slowly, and the pattern of these velocities traced the underlying structure. Radio astronomy opened entirely new investigative pathways, starting in the 1930s and 40s. Radio waves, unlike visible light, could pass through the dust clouds that obscured much of the galaxy. Hydrogen gas, the most abundant element in space, naturally emitted radio waves at a wavelength of 21 centimetres. By mapping this emission across the sky and measuring its Doppler shifts, astronomers could trace the spiral arms even in regions completely hidden from optical telescopes. For the first time, investigators could see through the galaxy's obscuring veils and map structures on the far side of the centre. Infrared observations added yet another layer. Starting in the 1960s, infrared detectors sensitive to heat rather than visible light revealed cool dust clouds and regions of star formation hidden in optical wavelengths. Young stars, still cocooned in the gas clouds from which they formed, shone brightly in infrared even while invisible to ordinary telescopes. Mapping these regions showed where the galaxy was actively creating new stars, tracing the spiral arms with different markers than optical or radio observations provided. Each wavelength revealed different aspects of the same structure. The investigation required not just instruments, but methods for measuring distances. Parallax, the apparent shift of nearby stars against more distant backgrounds as Earth orbits the Sun, provided the most direct distance measurements, but worked only for relatively close stars. For more distant objects, investigators developed a distance ladder, a series of techniques each calibrated against the previous rung. Parallax measured nearby stars. Those stars calibrated the brightness of certain variable stars. Those variables could be seen in star clusters, whose distances could then be determined, and so on outward in carefully linked steps. Each rung introduced uncertainties, but together they extended measurement capabilities across the galaxy. Cepheid variable stars became especially important in this investigative chain. These stars pulse regularly, brightening and dimming over periods of days to months, and their pulsation periods relate directly to their true luminosity. Henrietta Leavitt discovered this relationship in 1912 while studying Cepheids in the Magellanic Clouds. Her discovery gave investigators a standard candle, an object whose true brightness was known. By measuring how bright a Cepheid appeared and comparing to how bright it should be, distance could be calculated. This technique revolutionized galactic investigation, allowing reliable distance measurements across tens of thousands of light years. The investigation accelerated with space-based observatories, free from atmospheric distortion and able to observe wavelengths blocked by Earth's atmosphere. Space telescopes could see fainter objects and measure positions more precisely. The Hipparcos satellite, launched in 1989, measured parallaxes for over 100,000 stars with unprecedented accuracy. The Gaia spacecraft, launched in 2013, extended this to over 1 billion stars, creating a three-dimensional map of the Milky Way far more detailed than anything previously possible. Each spacecraft added immense data sets to the investigation, constraining the galaxy's size and structure with ever greater precision. Computer simulations became another investigative tool. As computing power increased, astronomers could model galaxy formation and evolution, testing whether their theories could reproduce observed properties. These simulations started with conditions shortly after the Big Bang and followed how dark matter clumped, how gas cooled and formed stars, how spiral arms developed, how mergers shaped structure. Comparing simulation results to real observations constrained possible models, narrowing the range of plausible galactic sizes and masses. Virtual investigations complemented physical observations. The pursuit also required international collaboration. No single observatory or researcher could measure everything needed. Telescopes in both hemispheres observed different parts of the galactic disk and halo. Radio arrays scattered across continents combined their signals to create effective instruments, thousands of kilometres wide. Data from multiple wavelengths had to be integrated, requiring coordination between optical, infrared, radio, and X-ray astronomers. The investigation became a global effort, transcending national boundaries in pursuit of understanding. Fieldwork added another dimension. Some investigators travelled to remote mountaintops, where dry air and minimal light pollution provided optimal observing conditions. Others journeyed to southern hemisphere sites to observe regions of the Milky Way invisible from northern latitudes. Still others coordinated networks of smaller telescopes scattered worldwide, monitoring variable stars and transient events. The investigation required not just sophisticated instruments, but the willingness to go wherever the sky was clearest, wherever crucial observations could be made. Data analysis consumed as much time as observation. Photographic plates had to be measured by hand or later with automated scanning equipment. Spectra required careful calibration to extract accurate velocities. Radio maps needed processing to remove interference and reveal faint signals. As datasets grew larger, investigators developed new statistical methods and computational techniques to extract meaning from millions of measurements. The pursuit involved as much work at desks and computers as at telescopes. The investigation continues today, ongoing rather than complete. New surveys map ever fainter stars, trace ever more distant gas clouds, measure motions with ever greater precision. Each generation of instruments pushes measurement capabilities farther, answering old questions while raising new ones. The pursuit of the galaxy's size has become an endless process of refinement, each improvement in technology or technique adding detail to the emerging picture. The investigation is not something that happened in the past, but an active present tense effort, a continuous reaching toward better understanding of the immense structure within which we live. The data that slowly revealed the Milky Way's true size came not in a single revelation, but as countless fragments, clues scattered across decades of patient observation. Each measurement was a piece of a vast puzzle, and only by gathering thousands of these pieces could astronomers begin to see the larger picture emerge. The data was messy, often contradictory, always incomplete, yet within it lay the truth about the galaxy's immense scale waiting to be decoded. Star catalogues formed the foundation of this data. Beginning in the 18th century, astronomers systematically recorded the positions and brightnesses of stars, creating lists that grew longer with each generation. The Bonner-Dirk-Musterung catalogue, compiled in the mid-1800s, contained over 300,000 stars. Later catalogues reached into the millions. Each entry was a data point, a tiny clue about galactic structure. Where stars clustered densely, where they thinned out, how their brightnesses distributed across the sky, all carried information about the galaxy's shape and extent. Distance measurements provided the most crucial data, but also the most difficult to obtain. Parallax observations measuring the tiny apparent shifts of nearby stars as Earth orbited the Sun could reach only the closest few thousand stars with 19th century instruments. Friedrich Bessel made the first successful parallax measurement in 1838, determining that the star 61 Cygni lay about 11 light-years away. This single data point established the scale for all subsequent measurements, providing the first rung on the cosmic distance ladder that would eventually span the galaxy. Proper motions, the slow drift of stars across the sky over years and decades, added another layer of data. By comparing photographs taken decades apart, astronomers could measure how stars moved relative to each other. These motions revealed that stars near the Sun shared common velocities, suggesting they moved together as part of a larger system. The data showed patterns, streams of stars flowing in particular directions, all consistent with rotation around a distant galactic centre. Each measured motion was a clue to the underlying structure and dynamics. Variable star data proved especially valuable. Certain stars changed brightness in regular patterns, pulsing over days or weeks. Henrietta Leavitt's painstaking measurements of Cepheid variables in the Magellanic Clouds established that their pulsation periods related directly to their true brightness. This relationship transformed these stars into standard candles, objects whose distance could be determined by comparing apparent brightness to known luminosity. Every Cepheid discovered and measured added a new distance marker, extending the map of galactic structure outward. Spectroscopic data revealed compositions and velocities. By analysing the specific wavelengths of light absorbed or emitted by stars, astronomers could determine what elements they contained and how hot they burned. More importantly, measuring shifts in spectral lines revealed how fast stars moved along the line of sight, approaching or receding from Earth. This velocity data, accumulated for thousands of stars, mapped the galaxy's rotation curve, showing how orbital speeds changed with distance from the centre. The data traced the gravitational influence of both visible and invisible mass. Radio observations generated entirely different data sets. Measurements of 21 centimetre hydrogen emission revealed vast clouds of gas spread throughout the galactic disk. The intensity of this emission showed where gas concentrated, tracing the spiral arms. The Doppler shifts of the radio signals indicated how the gas moved, rotating around the galactic centre. This data could penetrate dust clouds that blocked optical light, revealing structures on the far side of the galaxy previously hidden from view. For the first time, investigators had data spanning the entire galactic disk. Globular cluster data provided clues about the halo. These dense spherical collections of stars orbited high above the galactic plane, and measuring their distances required careful analysis of the stars they contained. RR Lyrae variables, pulsating stars similar to Cepheids, but less luminous, served as distance indicators within clusters. Data on dozens of globular clusters revealed they formed a roughly spherical distribution centred on a point far from the Sun, about 26,000 light-years towards Sagittarius. This data suggested the true galactic centre and provided the first reliable estimate of our distance from it. Dust extinction data added crucial corrections. Starlight passing through interstellar dust clouds grows dimmer and redder, making distant stars appear fainter and cooler than they truly are. Without accounting for this extinction, distance estimates could be wrong by factors of 2 or more. Data on dust distribution came from comparing star colours, from observing dark nebulae that blocked background stars, and later from infrared observations that could measure dust temperature and density directly. This correction data was essential for accurate measurements. Photometric data, careful measurements of star brightnesses in different wavelengths, revealed stellar populations. Young hot blue stars concentrated in spiral arms, while older cooler red stars spread more uniformly through the disk and bulge. The oldest stars, found in globular clusters in the halo, contained fewer heavy elements than younger stars, preserving the chemical signature of the galaxy's early generations. This population data traced the galaxy's history, showing how it grew and evolved, providing context for understanding its current size and structure. Velocity dispersion data showed how stars moved not just in organised rotation, but also in random motions up and down, in and out. These random velocities reflected the galaxy's gravitational potential, with faster dispersions indicating deeper gravitational wells. Data on velocity dispersions at different distances from the centre helped map the mass distribution, revealing the presence of dark matter in the halo through its gravitational influence on stellar motions, even though the dark matter itself emitted no light. The data was never perfect. Every measurement carried uncertainties, error bars that reflected the limits of instruments and techniques. Some stars were too faint to measure accurately. Some regions were too obscured by dust. Some distances relied on assumptions that might not hold. Comparing data from different sources often revealed discrepancies, measurements that disagreed by margins larger than their stated uncertainties. Reconciling these differences required judgment, deciding which data to trust and which to question, a process as much art as science. Modern datasets reached unprecedented scales. The Gaia spacecraft measured positions, proper motions and parallaxes for over 1 billion stars. Its data release in 2018 transformed galactic astronomy, providing a 3-dimensional map more detailed than anything previously possible. Individual stars could be tracked in their orbits. Streams from disrupted satellites could be traced. The warping of the galactic disk could be measured precisely. This single data set contained more information than all previous galactic surveys combined. Yet even with such comprehensive data, gaps remained. The galactic centre, obscured by dust and crowded with stars, was difficult to observe in optical light. The far side of the disk remained harder to map than the near side. The outermost reaches of the halo, where stars grew sparse and faint, pushed measurement capabilities to their limits. The dark matter halo, containing most of the galaxy's mass, could only be inferred indirectly through its gravitational effects. Complete data remained an aspiration rather than a reality. The data showed that the Milky Way was not simple. The disk was warped and flared at its edges. The spiral arms were not neat logarithmic curves but complex structures with spurs and branches. The halo contained streams and shells, remnants of past mergers. The rotation curve remained flat far into the outer disk, evidence of dark matter. Every new dataset revealed more complexity, more structure on smaller scales, More evidence that the galaxy was not an idealised mathematical object, but a messy, beautiful, evolving system. Astronomers learned to work with this imperfect data, to extract meaning from fragments, to build models that matched observations within their uncertainties. The data alone could not tell them the galaxy's size. It had to be interpreted compared to theories, tested for consistency. But without the data, without these countless clues and fragments accumulated over centuries, no theory could be confirmed or rejected. The data was the foundation, the empirical ground on which all understanding rested, the raw material from which knowledge of the galaxy's immense scale was painstakingly constructed. As data accumulated and theories refined, a deeper mystery emerged from beneath the surface of galactic astronomy. The visible structures, the stars and gas that telescopes could observe, represented only a fraction of the Milky Way's total mass. Something invisible, something that emitted no light across any wavelength, dominated the galaxy's gravitational field. This hidden component, eventually named dark matter, transformed understanding of the galaxy's size from a simple measurement of visible structures to a more complex question about invisible halos extending far beyond the reach of starlight. The first hints appeared in rotation curves, when astronomers measured how fast stars and gas orbited at different distances from the galactic centre. They expected to find speeds decreasing in the outer regions, following the same pattern that planets show in the solar system. Mercury orbits quickly, Neptune slowly, speed falling with distance from the Sun's mass. But galactic rotation curves remained flat far into the outer disk. Stars tens of thousands of light years from the centre orbited just as fast as those much closer in. This flatness contradicted expectations based on visible matter alone. The mathematics was straightforward but startling. To keep stars moving so quickly in the outer regions required more gravitational pull than visible stars and gas could provide. Either Newton's laws of gravity failed on galactic scales, a radical and disturbing possibility, or unseen mass was present, providing the additional gravity needed to explain observed motions. Most astronomers favoured the second explanation, but this raised profound questions. What was this invisible mass? How much of it existed? Where was it located? Estimates suggested that dark matter outweighed visible matter by factors of 5 or 10 to 1. Most of the Milky Way's mass was not in stars or gas, but in some unknown substance that interacted only through gravity. This hidden truth meant that measuring the galaxy's visible extent gave only a partial picture. The true gravitational reach of the Milky Way extended much farther, perhaps hundreds of thousands of light years into space, defined by dark matter rather than starlight. The nature of dark matter remained mysterious. It could not be ordinary matter like rocks or planets or failed stars, because such objects would still block or emit some form of radiation. The quantity needed would be visible in surveys. Dark matter had to be something more exotic, particles that passed through ordinary matter without interacting electromagnetically. Candidates included theoretical particles like WIMPs, weakly interacting massive particles, or axions, hypothetical particles with unusual properties. Despite decades of searching, none had been conclusively detected. Evidence for dark matter came from multiple independent observations. Gravitational lensing, where light from distant galaxies bent as it passed through the Milky Way's gravitational field, indicated more mass than visible stars could explain. The velocities of satellite galaxies orbiting the Milky Way implied a massive halo holding them in place. The motions of globular clusters high above the disk showed gravitational influence from unseen mass. Every line of evidence pointed to the same conclusion. Something invisible dominated the galaxy's mass budget. This deeper mystery reshaped understanding of galactic size. The visible disk, about 100,000 light-years across, represented only the luminous core of a much larger structure. The dark matter halo might extend 3 or 4 times farther, gradually fading until its influence merged with that of neighbouring galaxies. Defining where the Milky Way ended became arbitrary, a choice of threshold rather than a clear physical boundary. The galaxy was both smaller and larger than it appeared, depending on whether you counted light or gravity. The realisation that most of the galaxy was invisible carried philosophical weight. For all of human history, people had assumed that seeing was knowing, that the visible universe represented reality. Dark matter challenged this assumption. Most of the cosmos was hidden, detectable only through inference and indirect effects. The Milky Way that stretched luminously across the night sky was just the tip of an enormous invisible iceberg, the small fraction that happened to shine while the bulk remained eternally dark. Computer simulations helped visualize this hidden structure. When astronomers modelled galaxy formation starting from the early universe, dark matter clumped first, forming halos that attracted ordinary matter. Gas fell into these dark matter wells, cooled and formed stars, creating the visible galaxies we observe. But the dark matter remained, surrounding and permeating the visible structures. Simulated Milky Ways showed luminous disks embedded in vast diffuse halos, spherical clouds of invisible particles extending far beyond the stars. The deeper mystery also affected measurements of the galaxy's mass. Weighing the Milky Way required accounting for both visible and dark components. Early estimates based only on star counts severely underestimated the total. Modern estimates, incorporating rotation curves and satellite velocities, suggested the Milky Way contained 1 trillion or more solar masses, most of it dark matter. The galaxy was far heavier than it appeared, its gravitational influence correspondingly greater. Questions multiplied. Was dark matter uniformly distributed or clumped? Did it form streams like visible matter or remain smoothly spread? How far did the halo extend before the Andromeda Galaxy's dark matter took over? Could dark matter explain other mysteries like the warping of the galactic disk or unexpected stellar streams? Each answer spawned new questions, deeper layers of mystery beneath the already mysterious. Some researchers explored alternatives to dark matter, modified Newtonian dynamics, or MOND, proposed that gravity behaved differently at the very low accelerations present in galactic outskirts. This approach could explain rotation curves without invoking invisible mass. But MOND struggled to explain other observations like gravitational lensing, and required different modifications for different situations. Most astronomers remained convinced that dark matter, however mysterious, provided a more consistent explanation across all scales. The search for dark matter became one of astronomy's great quests. Detectors deep underground watched for rare interactions between dark matter particles and ordinary atoms. Satellites scanned for gamma rays that might be produced when dark matter particles collided and annihilated. Particle accelerators tried to create dark matter in collisions between protons. Despite enormous effort and investment, dark matter particles remained frustratingly elusive, present in their gravitational effects but absent in direct detection. Yet the mystery was productive. It drove technological innovation, spawned new theoretical frameworks, connected astronomy to particle physics in unexpected ways. Not knowing what dark matter was did not prevent using its effects to map the galaxy's structure. The mystery was acknowledged, incorporated into models, and used as a tool for understanding even while its fundamental nature remained obscure. The hidden truth about dark matter fundamentally altered the meaning of galactic size. The Milky Way was not just the stars you could see, but an enormous gravitational structure extending far into space. Its influence reached across hundreds of thousands of light years, binding satellite galaxies, shaping cosmic flows, defining a region of space dominated by its mass. The visible galaxy was like a city at night, with the lights marking where people lived. but the true extent included dark suburbs and countryside far beyond the illumination. To understand how big the galaxy truly was meant grappling with this deeper mystery, accepting that most of the answer lay hidden in darkness, invisible but undeniably real. The turning point in understanding the Milky Way's size came not from a single discovery, but from a convergence of new technologies and perspectives that fundamentally shifted how astronomers could observe and measure the galaxy. This paradigm shift occurred gradually through the late 20th and early 21st centuries as space-based telescopes, digital detectors, and global computational networks transformed astronomical practice. What had been impossible for previous generations suddenly became achievable, and the galaxy's true scale emerged with unprecedented clarity. The launch of space-based observatories marked the first major shift. Telescopes above Earth's atmosphere could observe wavelengths blocked by air, could see without atmospheric distortion, could stare at targets for hours without daylight interrupting. The Hubble Space Telescope, launched in 1990, revolutionized optical and ultraviolet astronomy. Later missions like Spitzer and Herschel opened infrared windows. Chandra and XMM Newton revealed X-ray sources. Each observatory added a new dimension to galactic observations, revealing structures and processes invisible from the ground. The Hipparcos satellite, launched in 1989, represented a turning point specifically for distance measurements. It measured parallaxes for over 100,000 stars with precision far exceeding ground-based capabilities. For the first time, accurate distances extended to thousands of light-years rather than just hundreds. The resulting three-dimensional map showed the local galactic neighbourhood in detail, revealing the structure of nearby spiral arms and establishing a firm foundation for more distant measurements. The era of guessing at galactic structure gave way to precise mapping. Digital detectors replaced photographic plates, another crucial shift. CCDs, charge-coupled devices, could detect individual photons with high efficiency across a range of wavelengths. They produced digital images that computers could analyse automatically, extracting positions and brightnesses of millions of stars from single exposures. Surveys that would have taken decades with photographic plates could now be completed in years. The volume of data exploded, requiring new computational approaches but providing unprecedented detail about galactic structure. The Sloan Digital Sky Survey, begun in 2000, exemplified this new approach. Using dedicated telescopes and digital cameras, it systematically mapped a quarter of the sky, measuring positions, colours, and spectra for hundreds of millions of objects. Though focused on distant galaxies and quasars, its data revolutionised understanding of the Milky Way's structure as well. Stellar populations could be analysed statistically. Faint halo streams became visible. The three-dimensional distribution of stars emerged from the data with clarity impossible before. Radio interferometry reached new scales as well. Networks of radio telescopes scattered across continents, or even globally, could combine their signals, creating effective instruments thousands of kilometres wide. This technique, called very long baseline interferometry, achieved angular resolutions finer than any optical telescope. Applied to galactic observations, it precisely measured distances to star-forming regions, traced spiral arm structures, and revealed details of the central black hole region. Radio astronomy matured from detecting basic features to mapping fine structure. The Gaia spacecraft, launched in 2013, represented perhaps the most significant turning point. Its mission was simple but profound: measure the positions, motions, and distances of as many stars as possible with extraordinary precision. Over its operating life, Gaia observed more than 1 billion stars, roughly 1% of the Milky Way's total population. For each, it measured position to better than millisecond accuracy, proper motion to track how stars moved across the sky, and parallax to determine distance. The resulting dataset transformed galactic astronomy. Gaia's data releases, beginning in 2016 and continuing through subsequent years, revealed the Milky Way in 3 dimensions with unprecedented detail. Spiral arms showed clearly in the spatial distribution of young stars. The galactic disk as warp became precisely measurable. Streams from disrupted satellite galaxies traced paths across the halo. Stellar velocities revealed the galaxy's rotation in exquisite detail. Every aspect of galactic structure came into sharper focus. What had been inferred now became directly observed. The paradigm shift extended to theoretical work as well. Computational power increased exponentially, allowing simulations of galactic evolution at resolution and scale impossible before. Modern simulations could follow billions of particles, representing both stars and dark matter, through billions of years of evolution. They could model spiral arm formation, satellite accretion, disk heating, and countless other processes. Comparing simulated galaxies to Gaia observations-constrained models, testing theories against data in ways previous generations could only dream of. Machine learning and artificial intelligence added new analytical capabilities. Algorithms could classify millions of stars automatically, identifying rare types or unusual objects. Neural networks could estimate distances from spectral features, extending measurements beyond Gaia's reach. Pattern recognition software could find subtle structures in distribution maps, streams and shells too faint for eye alone to detect. The analysis of massive datasets became as important as their collection. International collaboration reached unprecedented levels. Data from multiple missions and surveys could be combined, with observations at different wavelengths showing different aspects of the same structures. Astronomers worldwide contributed to databases and shared analysis tools. The investigation of the galaxy became truly global, transcending individual institutions or nations. The paradigm shifted from isolated researchers at single telescopes to collaborative networks spanning the planet. The shift also included changing definitions and frameworks. The galaxy's size was no longer described by a single number, but by multiple measurements: disk radius, disk thickness, halo extent, dark matter reach, each appropriate for different contexts. 3-dimensional maps replaced 2-dimensional projections. Dynamical models superseded static pictures. The Milky Way emerged as a complex evolving system rather than a fixed structure, its size a dynamic property changing over time as satellites merged and dark matter redistributed. Perhaps most profoundly, the paradigm shift changed what questions could be asked. Instead of simply asking how big the galaxy was, astronomers could now investigate how its size varied with cosmic time, how it grew through mergers, how its rotation affected star formation, how dark matter shaped visible structures. The basic question of size, once so difficult to answer, became just the starting point for deeper inquiries into formation, evolution, and future fate. This turning point did not mean all mysteries were solved. New observations raised new questions. Gaia revealed unexpected streams and structures requiring explanation. The dark matter distribution remained uncertain in details. The exact distance to the galactic centre still carried error bars. But the fundamental paradigm had shifted from uncertainty to refinement, from guessing to measuring, from isolated observations to comprehensive mapping. The galaxy's size was no longer unknown, but increasingly well determined, its boundaries traced with confidence even if absolute precision remained elusive. For those watching these developments, the transformation was breathtaking. Within a single generation, the Milky Way shifted from a partially glimpsed structure to a precisely mapped system. The paradigm shift represented not just technological advancement, but a change in perspective, a new way of seeing and understanding our galactic home. The turning point had been reached, and beyond it lay an era of detailed investigation that previous astronomers could barely imagine. When astronomers finally established the Milky Way's true scale, With reasonable confidence, the immediate consequences rippled through both scientific fields and popular consciousness. The numbers themselves, 100,000 light-years across the visible disk, hundreds of thousands more including the dark matter halo, containing hundreds of billions of stars, were so vast that they forced a recalibration of how humans understood their place in the cosmos. This was not merely an academic adjustment, but a profound shift in perspective that touched everything from scientific research programs to philosophical reflections on existence. The first consequence was practical and immediate. Understanding the galaxy's size allowed astronomers to place other cosmic objects in proper context. When a supernova exploded or a gamma ray burst flashed, knowing the galaxy's dimensions helped determine whether these events occurred within the Milky Way or in distant galaxies beyond. Distance scales that had been uncertain became reliable. The cosmic distance ladder that carefully constructed chain of measurements reaching from nearby stars to distant galaxies could be calibrated with new confidence once the Milky Way's structure was properly understood. Star formation studies benefited enormously. Knowing the true distances to nebulae and star clusters allowed accurate calculations of their sizes, masses and energy outputs. A nebula that appeared large on the sky might be nearby and small, or distant and immense. Only with proper distance measurements could astronomers determine which was true. Understanding the galaxy's scale meant understanding the true nature of objects within it, separating perspective effects from physical reality. The consequences flowed through every subfield that studied galactic phenomena. The revelation about dark matter's dominance had particularly profound consequences. If most of the galaxy's mass was invisible, then visible structures represented only a small fraction of the total system. This realization forced theorists to rethink galaxy formation and evolution. Models had to account for dark matter halos forming first, with visible matter falling into them later. The interplay between dark and visible matter shaped everything from spiral arm structure to satellite galaxy orbits. Understanding this hidden component became essential to understanding anything else about the galaxy. Philosophically, the galaxy's immense size immediately challenged human significance. If the Milky Way stretched across hundreds of thousands of light-years and contained hundreds of billions of stars, then our solar system occupied an infinitesimally small fraction of the whole. Earth, already known to be tiny compared to gas giants and the Sun itself, shrank further into cosmic insignificance. The consequence was a kind of existential vertigo, a realization that human affairs occurred on a stage so small as to be essentially invisible from any cosmic perspective. Yet this consequence cut both ways. Some found the galaxy's vastness diminishing, making human concerns seem trivial. Others found it liberating, realizing that cosmic scales placed daily stresses in perspective. If the galaxy stretched so far and existed so long, then personal failures and anxieties became less overwhelming. The consequence of understanding scale could be either nihilism or comfort, depending on one's philosophical orientation. Both responses emerged as the knowledge spread beyond astronomical circles into broader culture. Educational systems faced immediate consequences as well. Textbooks needed revision. Planetarium shows required updates. Public understanding of the cosmos had to adjust to include the Milky Way's true dimensions. Teachers explained that we lived not at the centre of everything, but in the outer regions of an enormous disk. That most of what surrounded us was invisible. That even our impressive galaxy was just one among billions. These lessons reshaped how new generations understood their cosmic context from an early age. The search for extraterrestrial life gained new urgency as a consequence of understanding galactic scale. With hundreds of billions of stars, many hosting planets, the probability of life elsewhere seemed to increase. If even a tiny fraction of stars had habitable worlds, the Milky Way might teem with life. This consequence sparked renewed interest in SETI, the search for extraterrestrial intelligence, and motivated missions to study exoplanets. the galaxy's vastness transformed from an abstract number into a landscape of possibilities, each star a potential home for other beings. Conversely, understanding the distances involved highlighted the challenge of ever contacting alien civilizations. If the nearest intelligent life existed thousands of light years away, communication would require millennia for messages to travel back and forth. Physical travel seemed even more daunting. The consequence was a paradox. The galaxy's size made life elsewhere seem probable, but also made contact seem nearly impossible. This realization shaped discussions about humanity's future in space and our prospects for joining a galactic community. Scientific funding patterns shifted as a consequence of the new understanding. Missions to map the galaxy in greater detail received support, justified by the framework of knowledge that now existed. The Gaia spacecraft, dedicated to measuring stellar positions, secured funding partly because the galaxy's basic structure was understood well enough to know what needed refining. Consequences flowed through institutional channels, affecting which projects received resources and which directions research took. The aerospace industry felt consequences too. Understanding where we are in the galaxy helped calibrate spacecraft trajectories and understand interstellar space beyond the solar system. The Voyager probes, having left the heliosphere, now travelled through the local interstellar medium. Knowing the galaxy's structure helped interpret the environment they encountered. Future missions to nearby stars, if ever attempted, would need to account for galactic rotation, the sun's motion through space, and the distribution of matter they would traverse. The practical consequences extended beyond pure science into engineering. Cultural consequences appeared in art, literature, and media. Science fiction writers incorporated the Milky Way's true scale into their stories, crafting narratives that respected the vast distances and immense structures. Visual artists created works depicting the galaxy from various perspectives, trying to convey its size through image. Popular documentaries explained galactic structure to mass audiences, using computer graphics to visualize what could never be photographed directly. The knowledge rippled through culture, changing how the Milky Way appeared in collective imagination. Religious and philosophical traditions grappled with consequences for their worldviews. Some saw the galaxy's immensity as evidence of divine creation, a structure so vast only a cosmic intelligence could have designed it. Others found in its scale an argument for naturalism, showing that matter and energy self organised into structures far beyond any human purpose. The consequence for theology and philosophy was ongoing debate about meaning and significance in a universe of such incomprehensible extent. Psychologically, individuals responded variously to understanding galactic scale. Some experienced a sense of wonder that enhanced their appreciation of existence. Others felt overwhelming insignificance that bordered on despair. Still others remained largely unaffected, their daily lives unchanged by abstract knowledge of distant structures. The immediate ripple of consequence reached different people differently, transforming some perspectives profoundly while leaving others untouched. The human response to cosmic scale proved as varied as humanity itself. Within astronomy, subdisciplines reorganized around the new framework. Galactic astronomy solidified as a distinct field with its own conferences, journals, and career paths. Studies of the Milky Way's spiral structure, its central black hole, its satellite system, and its halo all flourished as understood context allowed focused investigation. The consequence was specialization, researchers dedicating entire careers to understanding specific aspects of galactic structure that previous generations could barely observe. Perhaps the most profound immediate consequence was simply confidence. After centuries of uncertainty and debate, astronomers could finally assert with reasonable assurance how big the galaxy was. This confidence provided a stable foundation for further investigation. Questions about galactic evolution, about the formation of spiral arms, about interactions with satellites, all could be addressed with greater rigour once the basic scale was established. The consequence was accelerated progress across multiple research frontiers, each building on the solid ground of measured dimensions. The impact of understanding the Milky Way's true size extended far beyond immediate consequences, echoing through time to reshape how humanity understood its past, present, and future. This was not just a scientific achievement, but a transformation in consciousness, a shift in the human story that reverberated across generations. The scale of the galaxy, once established, became woven into the fabric of how people thought about existence itself, influencing fields as diverse as cosmology, astrobiology, philosophy, and even poetry. In cosmology, the Milky Way's measured size provided a crucial calibration point for understanding the broader universe. If our galaxy stretched 100,000 light-years across and contained several hundred billion stars, what did that imply about the billions of other galaxies scattered through space? The impact was a deeper appreciation of cosmic scale. The observable universe, stretching tens of billions of light-years in all directions, contained perhaps 2 trillion galaxies, each comparable to or larger than the Milky Way. The numbers grew so large they lost conventional meaning, yet they were grounded in the careful measurement of our own galaxy's dimensions. The impact on astrobiology was equally profound. Understanding that the Milky Way contained hundreds of billions of stars, many with planetary systems, transformed estimates of where life might exist. The Drake equation, which attempted to calculate the number of intelligent civilizations in the galaxy, depended critically on knowing how many stars existed as potential hosts. With the galaxy's size and stellar population established, the equation's first term became reliable. Even conservative estimates suggested billions of potentially habitable worlds. The impact was a shift from viewing life as possibly unique to viewing it as potentially abundant, scattered across immense distances but likely present somewhere in the vast galactic expanse. Philosophically, the impact touched on fundamental questions about meaning and purpose. If the galaxy was so large that light took 100,000 years to cross it, and if it was just one among trillions of similar structures, what did that imply about human significance? Some philosophical traditions embraced the smallness, arguing it revealed the absurdity of claiming cosmic importance. Others found meaning precisely in consciousness, arising to comprehend such vastness, suggesting that awareness itself was the universe's way of knowing itself. The debate continues, but understanding galactic scale irrevocably shaped its terms. The impact on human imagination was visible in literature and art. Writers crafted stories set against the backdrop of galactic civilization, with characters traversing the spiral arms or encountering alien species from distant star systems. Artists created visualizations of the Milky Way, trying to convey its scale and beauty through image and metaphor. The galaxy became a canvas for human creativity, a space vast enough to contain any dream or nightmare. Science fiction matured from naive adventure stories into more sophisticated narratives that respected the immense distances and timescales involved. Educational institutions felt the impact across generations. Children growing up after the galaxy's size was established learned from an early age that they lived in a specific location within a measurable structure. Geography expanded to include galactic coordinates. The Milky Way became part of basic scientific literacy, as familiar as knowing the continents or understanding the solar system. This knowledge shaped how successive generations thought about their place in the cosmos, normalizing what previous generations had found almost incomprehensible. The impact on space exploration philosophy was significant. Understanding the galaxy's scale highlighted both the potential and the challenges of expansion beyond Earth. The nearest stars, several light years away, represented journeys of decades or centuries with foreseeable technology. The far reaches of the galaxy, tens of thousands of light years distant, seemed forever beyond reach. This realization tempered some of the unbounded optimism of early space-age thinking, replacing it with more realistic assessments of what interstellar civilization might actually entail. the impact was a maturing of human aspirations grounded in physical reality. Theologically, different traditions responded to the galaxy's scale in various ways. Some saw in its vastness evidence of divine power and creativity. A god who could create such immensity was beyond human comprehension, worthy of awe and worship. Others found the scale challenging to traditional notions of divine providence. If God cared about individual humans, why create a universe where humanity occupied such an infinitesimally small corner? These theological impacts continue to generate debate and reinterpretation of religious text in light of cosmic understanding. The impact on time perception was equally profound. Understanding that the galaxy took hundreds of millions of years to rotate once, that stars lived for billions of years, that structures evolved on timescales dwarfing human history, fundamentally altered conceptions of time itself. Human civilization, perhaps 10,000 years old, represented a fleeting moment in galactic history. Even human species' existence, a few 100,000 years, was barely a blink. This temporal impact created perspectives that could make current events seem simultaneously urgent and insignificant, important in the moment but invisible from cosmic viewpoints. Scientific methodology itself felt the impact. The techniques developed to measure the galaxy, from parallax to standard candles to spectroscopy, became templates applied throughout astronomy. The careful construction of the cosmic distance ladder, building from nearby measurements to distant ones, exemplified how to approach problems of scale systematically. The impact extended beyond galactic studies, influencing how astronomers investigated everything from local stellar neighbourhoods to the most distant visible galaxies. Methods proven measuring the Milky Way transferred to measuring the universe. The impact on human psychology appeared in unexpected ways. Awareness of galactic scale could trigger experiences ranging from existential dread to transcendent wonder. Psychologists documented something called the overview effect, originally observed in astronauts viewing Earth from space, but also reported by people contemplating galactic scale. This shift in perspective could be transformative, changing priorities and values, reducing anxiety about daily concerns, increasing feelings of connection to something larger than self. The impact was personal and varied, but repeatedly documented. Cultural narratives about human destiny evolved in response to understanding galactic scale. Grand visions of humanity spreading across the stars had to account for the actual distances and challenges involved. More modest scenarios focused on exploring nearby systems or communicating rather than travelling. Some narratives embraced the limitation, finding meaning in humanity's local neighbourhood. Others maintained faith in future technologies that might overcome distance constraints. The impact was ongoing negotiation between aspiration and reality, dreams and physics. The impact also included humility. Previous ages had placed Earth at the centre of everything, then the Sun, then at least the galaxy. Understanding that the Milky Way was one galaxy among countless others, and that we occupied an unremarkable location within it, completed the Copernican revolution. Humanity was not central, not special in location, not unique in cosmic perspective. This humbling impact could be difficult to accept but also liberating, freeing humans from need to maintain cosmic importance and allowing appreciation of existence on its own terms. Long-term impacts on scientific research directions became clear over decades. Understanding galactic structure enabled studies that would have been impossible without that foundation. Research into galaxy formation and evolution, into the role of dark matter in cosmic structure, into the potential for life throughout the universe, all built on the careful measurement of the Milky Way's size and properties. The impact multiplied through time as each generation of researchers used established knowledge to push boundaries further, asking new questions enabled by old answers. The impact ultimately was about context. Understanding the galaxy's size gave humanity a context for existence, a framework within which to situate ourselves. This context was both humbling and exhilarating. showing our smallness but also our participation in structures of immense beauty and complexity. The echoes of this understanding continue to reverberate, shaping how people think about past, present and future, about meaning and purpose, about what it means to be small beings in a vast cosmos contemplating their own tiny place within galactic immensity. Behind every measurement and calculation that revealed the Milky Way's true size stood human beings, individuals who dedicated their lives to answering this seemingly impossible question. These dreamers, as they might be called, were not superhuman, but ordinary people possessed by extraordinary curiosity. They endured cold nights at telescopes, decades of painstaking calculations, professional setbacks and personal sacrifices, all driven by the desire to know how big our galaxy truly was. Their stories, often overlooked in favour of the data they produced, reveal the human dimension of cosmic discovery. Henrietta Swan Leavitt exemplifies this human element perfectly. Working at Harvard College Observatory in the early 1900s, she was employed as a human computer, one of many women hired to analyse photographic plates for male astronomers. Her job was considered routine, even menial by the standards of the time. Yet in studying variable stars in the Magellanic Clouds, she discovered the period luminosity relationship of Cepheids, arguably the most important tool for measuring galactic distances. Her contribution was transformative, yet she received little recognition during her lifetime. She died in 1921, before the full impact of her work became clear. Her story reminds us that the dreamers were not always famous, not always rewarded, but their dedication changed everything. Harlow Shapley brought fierce determination to the question of galactic size. Working at Mount Wilson Observatory in California, he systematically measured distances to globular clusters, using them to map the Milky Way's halo. His conclusions, published in 1918, suggested a galaxy far larger than previously thought, with the Sun far from its centre. Shapley faced intense criticism from colleagues who found his estimates too radical. The debate became personal at times, with professional reputations at stake. Yet Shapley persisted, convinced by his data even when others doubted. His determination, his willingness to stand by measurements that challenged consensus, embodied the dreamer's commitment to truth over comfort. Vera Rubin brought both brilliance and persistence to understanding galactic rotation. Working in the mid-20th century, she faced barriers as a woman in astronomy, denied access to certain telescopes and opportunities available to male colleagues. Despite these obstacles, she produced meticulous measurements of galaxy rotation curves that provided some of the strongest evidence for dark matter. Her work on the Milky Way and other galaxies revealed the hidden mass that dominates cosmic structures. Rubin's story illustrates how dreamers often had to overcome not just scientific challenges, but social barriers, yet continued pursuing understanding despite discouragement. Jan Oort embodied the international dimension of galactic studies. Working from the Netherlands, he used radio astronomy to map the Milky Way structure, pioneering techniques that could pierce through obscuring dust. His work in the mid-20th century established the galactic centre's location and refined estimates of the galaxy's rotation. Oort's career spanned decades, through world wars and technological revolutions, and he adapted his methods as new tools became available. His longevity in the field showed how measuring the galaxy was not a sprint but a marathon, requiring sustained effort across an entire professional lifetime. The human element also includes the unsung assistants and technicians whose work made observations possible. Carolyn Herschel, sister of William Herschel, spent decades recording her brother's observations of stars and nebulae, making discoveries of her own but rarely receiving credit. Countless observatory staff maintained telescopes, prepared photographic plates, developed films, all essential tasks without which the dreamer's visions could never have been realised. The measuring of the galaxy was collective work, depending on many hands even if only a few names entered history books. Modern dreamers like Anthony Brown leading the Gaia Data Processing Consortium continue the tradition. Transforming raw data from the Gaia spacecraft into usable star catalogues requires coordination among hundreds of scientists across multiple countries. Brown and his colleagues spend years developing software, testing algorithms, validating results. Their work lacks the romantic appeal of solitary genius making breakthrough discoveries, yet it is equally essential. The human element in contemporary astronomy is collaborative, distributed, dependent on teams rather than individuals, but driven by the same curiosity that motivated earlier generations. What united these dreamers across centuries was a particular kind of imagination. They could look at dots on photographic plates or numbers in notebooks and see vast structures stretching across space. They could envision the galaxy as a whole even while trapped within it, could mentally construct what could never be directly observed. This imaginative capacity, the ability to build cosmic understanding from fragmentary evidence, was their defining characteristic. They dreamed not of impossible things, but of things too large to see, using science to make those dreams concrete. The dreamers also faced doubt, both external and internal. Many spent years on measurements that led nowhere, on techniques that proved flawed, on theories that data eventually contradicted. They published papers that were ignored or criticised, applied for funding that was denied, made predictions that were wrong. The path to understanding the galaxy's size was littered with false starts and blind alleys. What distinguished the successful dreamers was not that they avoided mistakes, but that they persisted through them, learning and adjusting rather than abandoning the quest. Personal sacrifices accompanied the pursuit. Long nights at telescopes meant time away from families. Years spent on single problems meant opportunities in other fields foregone. Some dreamers never achieved the recognition they deserved, their contributions understood only in retrospect. Others saw their life's work superseded by better measurements, or contradicted by new data. The human element includes this cost, the price paid by those who devoted themselves to a question that might never be fully answered in their lifetimes. Yet there was also joy in the pursuit. The dreamers left records of moments when data suddenly made sense, when patterns emerged from chaos, when years of effort crystallized into understanding. These moments of clarity, brief but brilliant, justified the struggles. Reading their papers and notebooks, you find traces of this excitement, the thrill of discovery breaking through cautious scientific prose. The human element includes these rewards, the satisfaction of contributing even incrementally to humanity's understanding of its galactic home. The dreamers were motivated by different things. Some sought fame and recognition, hoping their names would be remembered. Others pursued understanding for its own sake, indifferent to credit. Some were driven by religious awe, seeing in the galaxy evidence of divine creation. Others approached it as pure physics, beauty emerging from mathematical descriptions of nature. Some wanted to challenge existing theories, to overturn orthodoxy. Others simply wanted to refine measurements, to get the numbers right. The diversity of motivation enriched the field, bringing different perspectives and approaches to the same fundamental question. Gender and cultural barriers meant that many potential dreamers never had the chance to contribute. Brilliant minds were excluded from astronomy because of their sex, race, or national origin. We can only wonder what would have been discovered if everyone with ability and passion had been welcomed into the field. The human element includes these lost possibilities, the measurements never made, the insights never realized, because social structures prevented certain people from pursuing their dreams. Still, progress happened. Each generation built on the previous one's work, standing on shoulders of earlier dreamers to see a bit farther. The communal nature of science meant that even flawed contributions often contained useful elements that successors could refine. The human element in measuring the galaxy was thus cumulative, a collective endeavour spanning centuries, with each dreamer adding their piece to an enormous puzzle. Today's dreamers use different tools than their predecessors, but share the same fundamental curiosity. They analyse Gaia data, run computer simulations, write papers, and attend conferences. They are more diverse than earlier generations, coming from more countries and backgrounds, but they continue the tradition of dedicating careers to understanding cosmic structure. The human element persists, the drive to know how big the galaxy is and what that means for our place within it. The path to understanding the Milky Way's true size was not smooth, but contested at every step. For every measurement proposed, critics emerged to challenge methods, question assumptions, and offer alternative interpretations. This opposition was not obstruction, but essential scientific practice, the testing and refining of ideas through rigorous skepticism. Yet it also reflected human elements like professional rivalry, intellectual conservatism, and the difficulty of accepting conclusions that upended established views. The battle for truth about galactic scale was fought not just with telescopes and mathematics, but with words and reputations. Early opposition came from those who trusted their eyes over instruments. When Galileo reported that his telescope revealed countless stars in the Milky Way's band, some contemporaries refused to look through the device, convinced that what the unaided eye could not see was illusion or artifact. This resistance to telescopic evidence delayed acceptance of the Milky Way as a collection of stars. The opposition was partly philosophical, rooted in Aristotelian views about the perfection of celestial realms, but also reflected reasonable caution about trusting new technologies whose reliability was unproven. In the 18 and 1900s, opposition centred on different estimates of galactic size. When Harlow Shapley proposed a galaxy hundreds of thousands of light years across, Heber Curtis and others argued for much smaller dimensions. The disagreement was not mere stubbornness, but reflected genuine uncertainties in measurement techniques. Shapley's distances to globular clusters depended on identifying certain variable stars correctly, and assuming their properties matched similar stars in better studied regions. Critics questioned these assumptions, pointing out potential sources of error. The opposition forced Shapley to defend his methods rigorously, ultimately strengthening the case when his basic conclusions proved correct. The Great Debate of 1920 showcased opposition in structured form. Shapley and Curtis presented their competing models of the cosmos to the National Academy of Sciences, each marshalling evidence for their view. The debate was civil but intense, with both participants defending positions they had staked careers upon. Curtis's smaller Milky Way with external island universes eventually proved closer to truth than Shapley's isolated giant galaxy, yet both were partially right and partially wrong. The opposition between them illuminated the complexity of the question, showing how honest disagreement advanced understanding even when neither side had all answers. Interstellar dust became a major source of opposition and confusion. Some astronomers recognized that dust dimmed and reddened starlight, requiring corrections to distance estimates. Others minimized or ignored dust effects, leading to systematic errors. Disputes arose over how much extinction to apply, with different schools advocating different correction factors. Those who underestimated dust ended up with galaxies that were too small, while those who overcompensated got sizes too large. The opposition between these camps reflected not just different measurements, but different philosophies about how to handle uncertain corrections. Dark matter faced enormous opposition when first proposed. The idea that most of the galaxy's mass was invisible struck many as ad hoc, a desperate attempt to save theories rather than an honest conclusion from data. Opponents argued for alternative explanations, from modified gravity to errors in rotation, curve measurements. Fritz Zwicky's early work on missing mass in galaxy clusters was largely ignored for decades. Vera Rubin's rotation curves met with skepticism. The opposition insisted that such an extraordinary claim required extraordinary evidence, and even when evidence accumulated, resistance continued. Only overwhelming data from multiple independent observations finally overcame the opposition and established dark matter as scientific consensus. Methodological opposition persisted throughout the measurement history. Researchers using parallax measurements sometimes disagreed with those using statistical methods. Optical astronomers questioned radio results. Those studying stars disputed conclusions from gas dynamics. Each subdiscipline had its own techniques and assumptions, and cross-checking between them often revealed discrepancies rather than agreement. The opposition between different methodological schools forced careful examination of systematic errors and helped identify which techniques were most reliable for which purposes. Personal rivalries added heat to scientific opposition. Astronomers competing for resources, recognition, and historical legacy sometimes opposed each other's work more vigorously than pure science warranted. Priority disputes erupted over who first measured particular features or proposed certain models. National pride entered as well, with researchers from different countries championing their own observatories' results. While regrettable, these human factors were perhaps inevitable in high-stakes research, where reputations and careers depended on being right. Conservative opposition came from those reluctant to abandon long-held views. Each expansion of the galaxy's estimated size required accepting that previous understanding was wrong, always difficult for those who had built careers on earlier models. Textbooks had to be rewritten, lectures revised, positions reconsidered. Some senior astronomers dug in against new measurements simply because accepting them meant admitting years of work had been based on incorrect scales. This opposition slowed progress, but also ensured that new ideas were thoroughly vetted before gaining acceptance. Instrumental skepticism provided another form of opposition. When new telescopes or detectors produced results conflicting with established measurements, critics questioned the instruments rather than the conclusions. Were space telescopes properly calibrated? Did CCD detectors introduce systematic errors? Were radio interferometers really measuring what they claimed? This skepticism was healthy, preventing premature acceptance of results that might contain unknown biases. But it also meant every technological advance faced an uphill battle gaining trust. The opposition between lumpers and splitters affected how the galaxy's size was defined. Lumpers wanted to include everything gravitationally bound to the Milky Way, extending the boundaries to incorporate dark matter, halos and distant satellites. Splitters preferred narrower definitions, counting only regions where stellar density exceeded clear thresholds. This definitional opposition meant the galaxy could be described as either 100,000 or nearly 1,000,000 light-years across, depending on your criteria. Both sides had valid points, and the opposition forced clarity about what exactly was being measured. Statistical opposition arose over error analysis and confidence levels. Some researchers reported measurements with tight error bars, claiming high precision. Others argued that systematic uncertainties were larger than acknowledged, preferring more conservative estimates. Disagreements about how to combine different data sets, how to weight contradictory measurements, and what confidence levels to require created ongoing opposition. The galaxy's size might be stated as 90,000 light-years by one group and 120,000 by another, both citing data but disagreeing on interpretation. The opposition ultimately served science well. Every challenged claim had to be defended with better evidence. Every disputed measurement prompted more careful analysis. The battle for truth about the galaxy's size, conducted through papers and conferences and sometimes heated debates, refined understanding in ways that unconsensus could never have achieved. Opposition forced precision where vagueness might have sufficed, demanded rigour where assumptions might have been accepted, and ensured that the final consensus rested on solid ground. Even today, opposition continues in more subdued form. Researchers debate the exact distance to the galactic centre, disagreeing by a few hundred light-years out of 26,000. They dispute the dark matter halo's extent, with estimates ranging by factors of 2. They question whether certain stellar streams are part of the Milky Way or independent structures. This ongoing opposition is healthy. showing that science remains self-critical, always questioning, never fully satisfied with current understanding. The battle for truth was never purely intellectual, but always involved human elements: pride, ambition, conservatism, rivalry. Yet through all the opposition, progress happened. The galaxy's size became known with increasing precision despite disagreements about details. The opposition refined rather than prevented understanding, serving as quality control on the path to truth. Those who opposed new ideas were not villains but necessary critics, ensuring that only well-supported conclusions gained acceptance. The battle was part of the process, conflict serving discovery. Something shifts when you truly internalise the Milky Way scale, when the numbers stop being abstract figures and start connecting to a deeper understanding of what they mean. This awakening, this transition from knowing intellectually to comprehending viscerally, marks a transformation in awareness. It is the moment when the galaxy becomes not just a measurement, but a felt reality. When you recognise that size is not merely distance, but encompasses time, motion, structure, and your own place within an incomprehensible vastness. This awakening changes how you see the night sky and your relationship to everything beyond Earth. The awakening often begins with contemplating a single fact until it penetrates beyond surface understanding. Consider that light from the far side of the galaxy, 100,000 light-years away, left its source before modern humans existed. The photons streaming across space began their journey when our ancestors were still evolving in Africa, when ice ages came and went, when entire civilizations rose and fell. Those photons are only now arriving, carrying information about a galaxy as it was in deep prehistory. To grasp this is to understand that size and time interweave, that the galaxy's spatial extent translates into temporal depth. Another awakening comes from understanding motion at galactic scales. The Sun orbits the galactic centre at hundreds of kilometres per second, yet takes 225 million years to complete one circuit. During the last galactic year, dinosaurs emerged, ruled Earth, and went extinct. Mammals evolved from small creatures into diverse forms. Continents drifted into new configurations. The solar system's position in the galaxy correlates with major events in Earth's history, though whether this connection is causal remains debated. To awaken to this timescale is to see human existence as a brief flicker within the galaxy's slow turning. The awakening includes recognizing that we are always moving, even when sitting still. Earth rotates on its axis at hundreds of meters per second at the equator. It orbits the Sun at 30 kilometers per second. The Sun orbits the galactic centre at more than 200 kilometers per second. The galaxy itself moves through the local group at still higher speeds. All these motions nest within each other, and we participate in all of them simultaneously without sensing any of it. To awaken to this constant motion is to realise that stillness is an illusion, that we swim through space even as we rest. Understanding the galaxy's structure brings another dimension of awareness. The disk, so vast that light takes 100,000 years to cross it, is only 1,000 light-years thick at the Sun's position. If you scaled the galaxy to the size of a dinner plate, the disk would be thinner than paper, a fragile structure spinning in darkness. Yet within that thin disk, hundreds of billions of stars orbit in rough alignment, held by gravity into a coherent system. The awakening here is to the remarkable organisation of matter on cosmic scales, the way chaos resolves into structure when gravity and motion achieve balance. The dark matter halo brings an awakening of a different kind. Most of what holds the galaxy together is invisible, interacting only through gravity. The stars and gas we observe represent a small fraction of total mass. The galaxy is mostly empty space, and even that space is mostly filled with something we cannot detect. To awaken to this is to recognise that direct sensory experience captures only a tiny slice of reality. The universe contains far more than meets the eye. and understanding requires looking beyond the visible into realms revealed only through inference and mathematics. An awakening occurs when you realise that every atom in your body was once part of the galaxy in a different form. The iron in your blood was forged in a dying star billions of years ago, scattered into space by a supernova, gathered into the cloud that became the solar system, incorporated into Earth, cycled through geological processes, taken up by plants, eaten and metabolized. You are recycled stardust, temporarily organised into conscious form. This awakening dissolves the boundary between self and cosmos, revealing that you're not in the galaxy but of it, made from its substance, participant in its cycles. The realisation of how many stars exist brings its own awakening. Hundreds of billions in the Milky Way alone means that if you counted one star per second, working day and night without rest, it would take thousands of years to count them all. Yet each one is potentially a sun to planets, perhaps to life. The sheer multitude awakens appreciation for abundance, for the profligacy of the universe in creating stars and worlds. It suggests that we are not alone, that somewhere in that vast collection of suns, other beings might be looking up at their own night sky wondering the same questions. The awakening includes understanding perspective. When you see the Milky Way stretching across the sky, you're looking through the disk from inside. The band of light is the combined glow of billions of stars too distant to resolve individually, smeared together by the limits of vision. You're seeing the galaxy edge on, like viewing a forest from within where nearby trees are distinct but distant ones merge into haze. This awareness transforms the Milky Way from a mysterious glow into an understandable structure, your view of it explained by geometry and position. Some awakenings are uncomfortable, recognizing that the sun occupies no special position, that we live in the galaxy's suburbs rather than near its centre, that our location is arbitrary and unremarkable, can feel diminishing. The Copernican revolution continues, each step removing humanity from privileged positions. Yet this awakening also brings freedom from anthropocentric thinking, permission to see the universe as it is, rather than as centred on human concerns. The discomfort passes, replaced by appreciation for being able to understand our actual place. The awakening to galactic rotation reveals order in apparent chaos. Stars do not move randomly, but follow paths determined by gravity, each orbiting according to its distance from the centre. The spiral arms, which seem fixed, are actually density waves passing through the disk like ripples on a pond. Stars move in and out of arms over time, but the wave pattern persists. This awareness shows that what appears static is actually dynamic, that the galaxy lives and breathes in slow motion, its structures flowing and reforming across millions of years. Another awakening comes from understanding that we can never step outside the galaxy to see it whole. All images of spiral galaxies are of other systems, not the Milky Way. Our knowledge comes from piecing together fragmentary views, like mapping a building from inside by looking through different windows. This limitation is fundamental, not technological. We will always be inside, always seeing part rather than whole. Yet from these parts, human ingenuity has constructed a remarkably complete picture. The awakening is to the power of inference, the ability to build cosmic understanding from limited perspective. The awareness extends to future time. The galaxy will change, its structure evolving as gas converts to stars, as satellites merge, as interactions with neighbours reshape the disk. In several billion years, the collision with Andromeda will transform everything, creating a new galaxy from the remnants of two. The sun may be flung into different regions, Earth's night sky unrecognisable. This awakening to impermanence shows that even structures as seemingly eternal as galaxies are temporary, processes rather than objects, patterns that persist for a time then dissolve into new forms. Some experience an awakening related to beauty. The Milky Way is not just a scientific object, but an aesthetic one. its spiral form pleasing to the eye, its scale inspiring awe. The mathematics describing it contain elegance. The images captured by telescopes reveal intricate structures of breathtaking complexity. This awakening to beauty in cosmic phenomena suggests that the universe is not only comprehensible, but also worth appreciating for its own sake, beyond any practical utility that understanding might bring. The awakening includes recognizing the achievement of measuring something so vast from within. Previous generations had no idea the galaxy was so large, or that we occupied such an unremarkable position. The fact that humans figured this out using mathematics and careful observation, overcoming enormous technical challenges, represents a triumph of intelligence and persistence. This awakening is to human capability, to what can be accomplished when curiosity drives systematic investigation across generations. Perhaps the deepest awakening is to interconnection. The galaxy is not a collection of separate objects, but an integrated system where everything influences everything else through gravity. Stars disturb each other's orbits, gas clouds collide and trigger star formation, supernova shock waves compress surrounding material, dark matter shapes visible structures. The whole is, more than the sum of parts, an emergent system whose behaviour cannot be understood by studying components in isolation. This holistic awareness mirrors insights from other fields, suggesting that reality at every scale is characterised by relationship and interaction rather than isolated independence. The new awareness that comes from truly comprehending the galaxy's size is not purely intellectual but existential. It changes how you experience being alive, how you relate to earth and sky, how you think about time and space and your brief moment within them. The awakening is irreversible. Once you genuinely understand the scale, you cannot return to seeing the night sky as a simple backdrop. It becomes a window into vast structures of which you're an inseparable part, made of their substance, shaped by their processes, tiny but also profoundly connected to everything that stretches beyond sight into the measureless dark. The deepest truth about the Milky Way's size is not found in any single number, but in what those numbers reveal about the nature of reality itself. This revelation transcends measurement to touch something fundamental about existence. The galaxy is bigger than we thought, yes, but more importantly it is bigger in ways that challenge our basic assumptions about space, matter, time, and consciousness. The deepest truth is not just quantitative but qualitative, showing that the universe operates on principles and scales that human intuition never anticipated and can barely grasp even now. The revelation begins with dark matter. When astronomers finally accepted that most of the galaxy's mass was invisible, it was not simply adding another component to their models. It was acknowledging that reality contains entire categories of substance fundamentally different from everything we experience directly. Dark matter does not emit light, does not absorb it, does not interact electromagnetically. It is felt only through gravity, warping space around it, holding galaxies together through invisible bonds. This revelation means that what we see is a small minority of what exists, that the visible universe is an island in an ocean of darkness. The deepest truth extends to the nature of measurement itself. We can never observe the Milky Way from outside, can never gain the external perspective that would make its size obvious. Everything we know comes from internal observations, from measuring within the system we are trying to understand. Yet from this limited viewpoint, using mathematics and careful inference, we have constructed an accurate model of galactic structure. This revelation is epistemological, showing that consciousness can transcend its limitations, that awareness trapped in one location can still comprehend the whole through thought and systematic observation. Another deep truth concerns time and causation. The galaxy's structure today results from processes stretching back billions of years. Dark matter clumped first, forming gravitational wells. Gas fell into these wells, cooled, fragmented, and formed stars. Some stars exploded, enriching the gas with heavy elements. New generations formed from this enriched material. Spiral arms emerged from gravitational instabilities in the rotating disk. Satellites merged, adding their mass and stars. Every feature we observe is the outcome of a long causal chain, each event influenced by preceding events in an unbroken sequence back to the Big Bang itself. The revelation includes the realization that size is relative and definition dependent. Is the Milky Way 100,000 light-years across or nearly a million? Both answers are correct depending on what you count. The visible disk gives one boundary, the dark matter halo another. There is no single right answer because galaxies do not have sharp edges. They fade gradually into intergalactic space, their influence decreasing but never quite reaching zero. This truth challenges human desire for precise boundaries and clear categories, showing that nature often operates in gradients rather than discrete steps. The deepest truth about stellar populations reveals galactic history. The oldest stars, found in globular clusters in the halo, formed more than 12 billion years ago from gas containing almost no heavy elements. Intermediate age stars in the thick disk show moderate enrichment. Young stars in the thin disk and spiral arms contain much higher fractions of carbon, oxygen, iron, and other elements heavier than helium. This chemical gradient records the galaxy's evolution, showing how successive generations of stars enrich the interstellar medium, how the galaxy grew from simple beginnings to chemical complexity. We are products of that enrichment, literally made from the ashes of ancient stars. The revelation extends to the connection between local and cosmic scales. The Milky Way's size and structure are not isolated facts, but connect to the broader universe's properties. The amount of dark matter, the rate of star formation, the presence of a central black hole, all these features appear in other galaxies as well, following statistical patterns. Our galaxy is typical, one example of a common type. This universality suggests that the same physical laws operating here apply throughout space, that understanding the Milky Way provides insight into galactic evolution generally. The local illuminates the universal. Perhaps the most profound revelation concerns consciousness itself. The galaxy, vast and ancient as it is, produced conditions allowing the formation of a planet where life emerged and evolved into beings capable of understanding galactic scale. From the galaxy's substance arose awareness that could measure the galaxy, comprehend its size, wonder at its existence. This seems almost impossible, that matter organised by gravity and nuclear physics could become conscious and reflective. Yet it happened, and the fact that you can contemplate the galaxy's size proves it. The deepest truth may be that the universe is not only large but also capable of producing awareness of its own largeness. The revelation includes understanding that our existence is improbable, yet inevitable. Given enough stars and planets, given billions of years for chemistry to experiment, the emergence of life somewhere becomes likely even if any individual world's odds are small. The galaxy's size directly relates to life's possibility. With only a few million stars, the chance of life emerging might be negligible. With hundreds of billions spread across 100,000 light-years, the probability becomes significant. Scale creates opportunity. Vastness allows rare events to occur somewhere even if they remain rare everywhere. Another deep truth involves the incompleteness of knowledge. Despite centuries of investigation, despite sophisticated instruments and detailed models, much about the galaxy remains unknown. The exact distance to the centre carries uncertainty. The dark matter's composition is mysterious. The full census of stars is incomplete. The future evolution depends on unknowable factors. This revelation that even after so much progress we still see through a glass darkly, that complete understanding may be forever beyond reach, is both humbling and honest. Science provides better and better approximations, but perhaps never final, perfect knowledge. The revelation touches on humanity's place not just in space but in time. The galaxy existed for billions of years before the solar system formed. It will continue for billions more after the sun dies. Our entire species' existence, from first emergence to final extinction whenever that occurs, represents a tiny fraction of galactic history. We are temporally peripheral, as well as spatially so. This truth could be crushing, rendering human concerns insignificant. Or it could be liberating, placing our anxieties in perspective, showing that the galaxy's endurance transcends any local catastrophe. The deepest truth also includes the realization that we are made of recycled material. Every atom heavier than hydrogen or helium was created in stars, most in supernova explosions. The calcium in our bones, the iron in our blood, the carbon forming our DNA, all were forged in stellar furnaces billions of years ago, scattered into space, gathered into new clouds, incorporated into the solar system, and eventually into us. We are not separate from the galaxy, but temporary arrangements of its substance, patterns that persist briefly before dissolving back into the cosmic recycling stream. The revelation extends to connection across scales. Quantum mechanics governs atomic behaviour. Chemistry shapes molecular interactions. Biology organises molecules into life. Consciousness emerges from biological systems. And all of this occurs within the gravitational architecture of the galaxy, which itself is part of the cosmic web stretching across the universe. The deepest truth is that reality is layered, with processes at each scale influencing and enabling processes at other scales, creating a nested hierarchy of phenomena from smallest to largest, from briefest to most enduring. Finally, the revelation includes the possibility of other awareness. If the Milky Way contains hundreds of billions of stars and planets are common, and life emerges where conditions allow, then we are probably not alone. Somewhere in the galaxy's vastness, other beings may exist, perhaps wondering about the same questions, perhaps vastly more advanced than us, perhaps just emerging into consciousness. This possibility transforms the galaxy from a collection of inanimate objects into a potential community of minds. The deepest truth may be that the galaxy is not just large, but alive, not just with simple organisms, but with intelligence and awareness scattered across its arms. The revelation is ongoing, not complete. Each generation discovers new layers of truth about the galaxy's size and nature. What we understand now will be refined or revised by future observations. The deepest truths we currently grasp may be shallow compared to insights that await discovery. Yet the process itself, the capacity to ask questions and pursue answers, to build understanding step by step, to approach truth asymptotically, even if never reaching it completely, this process reveals something profound about both the galaxy and ourselves. We are part of reality capable of understanding reality, consciousness comprehending the cosmos that created it. As our journey through the Milky Way's immensity draws toward its close, we find ourselves returning to where we began, but changed by what we have learned. The pale band stretching across the night sky no longer appears as simple mystery, but as understood structure, a disk of stars seen edge on, a home galaxy measured and mapped with increasing precision. Yet even with knowledge, wonder remains. Perhaps it deepens, enriched rather than diminished by understanding. The legacy of learning the galaxy's true size extends beyond facts into how we see ourselves and our place within the cosmos. The legacy lives on in every subsequent generation that grows up knowing these truths. Children today learn from early ages that we live in a galaxy 100,000 light-years across, that hundreds of billions of stars surround us, that most of the galaxy's mass is invisible dark matter. This knowledge shapes their worldview from the start, giving them cosmic context that previous generations lacked. They are citizens not just of Earth or nations, but of the Milky Way, aware of their galactic address from childhood. This educational legacy ensures that understanding of scale becomes part of human heritage, passed down and refined by each succeeding wave. The scientific legacy continues in ongoing research, Every year brings new measurements, better data, refined models. The Gaia spacecraft continues mapping stellar positions and motions. New telescopes pierce deeper into the galaxy's structure. Computer simulations grow more sophisticated, testing theories against observation with increasing rigour. The work of measuring the galaxy never truly ends, but becomes an ongoing process of refinement, each generation building on previous foundations to push understanding slightly farther. The legacy is not a finished product, but a living tradition of inquiry. The technological legacy extends beyond astronomy. Techniques developed to measure galactic distances found applications in other fields. Digital image processing, statistical analysis of massive data sets, methods for extracting signals from noise, all evolved partly from astronomical needs, and then spread to medicine, communications, and countless other domains. The legacy of measuring the galaxy includes these practical applications, ways that pure curiosity about cosmic scale led to tools benefiting humanity in unexpected ways. The philosophical legacy touches how humans think about existence and meaning. Knowing the galaxy's size places human life in context, showing both our insignificance in space and time and our remarkable capacity for understanding. This dual awareness, of being simultaneously tiny and comprehending, shapes contemporary philosophy and theology. Thinkers grapple with what it means to be small beings in vast cosmos, arriving at varied conclusions but all working from shared knowledge of actual scale. The legacy influences not just what we know, but how we interpret what we know. The artistic legacy appears in countless works inspired by galactic scale. Photographers capture the Milky Way arching over dark landscapes, connecting Earth to cosmic context. Visual artists create representations of spiral structure, trying to convey size through composition and colour. Writers craft stories set against backdrops of galactic exploration, using the known scale as framework for imagination. Musicians compose pieces evoking cosmic vastness. The legacy enriches culture, providing new sources of beauty and inspiration drawn from scientific understanding. The legacy includes the observatory, where you might go to see the Milky Way clearly, far from city lights. Dark sky preserves and dedicated viewing sites preserve access to the night sky, as it appeared to our ancestors before artificial illumination drowned out faint stars. These places become pilgrimage destinations where you can personally witness the galactic glow and reflect on its meaning. The legacy is not just knowledge but experience, the continued ability to see what inspired the questions that led to understanding. As we return from contemplating the galaxy's vastness to immediate awareness, the transition feels natural rather than jarring. The cosmic perspective does not erase daily life, but frames it, providing context without negating importance. You can hold both scales in mind simultaneously, appreciating how small concerns matter even within immense structures, how brief existence has value even against billions of years. The return is not retreat, but integration, bringing cosmic awareness back into ordinary experience. The legacy reaches into the future as well. Humanity's descendants, if we have any, will inherit this knowledge and build upon it. Perhaps they will spread beyond Earth, establishing presence in multiple star systems, becoming truly galactic civilization. Or perhaps they will remain local, exploring their cosmic neighbourhood while respecting the distances that make interstellar expansion challenging. Either way, they will carry forward understanding of the galaxy's size, this knowledge becoming foundation for whatever comes next in human or post-human development. The return to present moment includes gratitude for the journey. We have wandered together across light years and billions of years, through visible structures and invisible halos, following threads of measurement and meaning. We have met the dreamers who dedicated lives to answering seemingly impossible questions. We have witnessed battles between competing theories, seen how opposition refined understanding. We have reflected on what it all means, this knowledge of living within something so vast yet so structured. The legacy is also in the questions that remain. How far does the dark matter halo truly extend? What lies in the galaxy's most distant reaches? How will the collision with Andromeda unfold in detail? What forms will future star formation take? Do other civilizations exist somewhere in the galactic vastness? These unanswered questions ensure that the legacy is not closed but open, inviting further investigation, promising more discoveries for those who continue the work. As you return now to the simple awareness of lying beneath the stars, breathing slowly, letting thoughts drift like clouds, the galaxy remains above you, unchanged by your knowledge of it, but changed in how you perceive it. The band of light is both what it always was and something new, mystery and understanding woven together. You're small, yes, but also connected, made of the galaxy's substance, participant in its ongoing story, carrier of awareness about its nature. The closing brings us full circle to that opening invitation to let curiosity rest while the mind wanders gently through cosmic landscapes. We have asked how big the galaxy is and found answers, not single numbers but ranges and contexts, not just distances but meanings. The question seemed simple at the start but unfolded into layers of complexity and wonder. Now as we close, the simplicity returns, enriched by what lies behind it. The legacy endures in the night sky, in the data archives, in textbooks and papers, in the minds of those who understand. It endures in the sense of place that comes from knowing your galactic coordinates, from recognizing that you orbit a star that orbits a center, tens of thousands of light years away. It endures in the capacity to look up and not just see stars but comprehend structure, to recognize patterns and trace their causes, to feel both small and part of something magnificent. And so we return to rest, to the quiet breathing and the soft drift towards sleep, carrying with us the knowledge of galactic scale. The Milky Way stretches above and around us, vast and ancient, beautiful and strange, measured yet still mysterious. We have journeyed through its dimensions and returned safely to this small moment, this single breath, this peaceful closing of eyes beneath a sea of stars. The galaxy holds us gently in its invisible arms, spinning slowly through the dark, and we spin with it, part of its rhythm, children of its substance, grateful for the chance to wonder and to understand, however incompletely, how big our galaxy truly is. Sleep now beneath the Milky Way, held by forces that stretch across light years, part of structures that endure for billions of years, yet also here, now, present in this moment of rest. The galaxy's size is both out there and within you, measured in light years and written in the atoms of your body. Good night, and may the vastness comfort rather than overwhelm, connecting you to something far larger while honouring the small precious life you live within its embrace.